Hello and welcome to Lesson 28 of Additional Maths with Mr. Barrow. Today we're going to be looking at logarithms and specifically solving equations using the logarithmic function. Okay, so from a previous lesson, so lesson 27, a reminder of some of the logarithmic laws that we will need in this lesson. Okay, so here are the log laws that you can split up a log of a multiple of two things into the log of two things added together. And you can split up a log of the division of two things as the log of those two things subtracted from each other. And also that if you multiply a logarithm by a constant, then that's the same as the logarithm of that same thing to the power of that constant. Okay, so those were all explained in a previous lesson, and we might be using some of them in today's lesson. So we want to be able to solve equations where the unknown is in the power. For example, this one. Solve this equation, giving your answer to three significant figures. 5 to the power of 2x plus 1 is 1,000. So here it's a question of finding what 2x plus 1 needs to be equal to. 5 to the power of something is equal to 1,000. I know with my logarithms that if I have a to the power of b equaling c, then a way of finding b, if I know a and c, is that b is worth the logarithm to base a of c. These two statements are equivalent. So b is the logarithm of c to base a. Okay, so a is the base of the power, c is the result of putting a to the power of b. So to get the answer, to get the power that you need, you do log base a of c. So it's the same for this question. So here, if I want to find what 2x plus 1 needs to be, I can rewrite this entire expression in terms of logarithms. So 2x plus 1 will be equal to the logarithm to base 5 of 1,000. This expression, log base 5 of 1,000, in essence, means what power do I put 5 to get 1,000? So that can be gained on my calculator. You can get a general sense of what it's going to be. You know, 5 squared is 25, 5 cubed is 125, 5 to the power of 4 is 625. So it'll be between 4 and 5. 5 to the power of 4 point something will be 1,000. But I'm going to keep my log base 5 of 1,000 because that's exact rather than estimating it or putting it to one decimal place or something. So next, I just want to find what x is equal to. So I subtract 1 from both sides. So 2x is equal to log base 5 of 1,000, subtract 1. Remembering that the take away 1 is outside of the logarithm. Okay, so it's log base 5 of 1,000. It's not log base 5 of 1,000 take away 1. It's log base 5 of 1,000. Then you pause to dramatic effect. Then you subtract 1. So therefore, x is equal to half of all of that. Half of log base 5 of 1,000, dramatic pause, subtract 1, end brackets. And that, to three significant figures, your calculator will give you as 1.65. So if you substituted 1.65 in as x, then that expression would equal 1,000. Okay, so what you need now is to see if you can answer a similar problem. Okay, so I would like you to try and solve this equation here. So pause the video, solve this equation, write your answer to three significant figures. The equation is 7 to the power of 3x minus 2 is equal to 842. Okay, I'll go through the answer now. So firstly, you know that 3x minus 2 is equal to log base 7 of 842. And then you add 2 to both sides, so 3x is equal to log base 7 of 842, dramatic pause, add 2. And then x is equal to a third of all of that. A third of log base 7 of 842 plus 2, which is, to three significant figures, 1.82. If you got that right, superb. Okay, let's go on with the next type. So the next type of equation, work example 2. Solve to three significant figures the equation 3 to the power of 5 minus x is equal to 2 to the power of 5 plus x. Now, this is very different to the previous question. We have two different bases here. We have a base which is 3 and a base which is 2. So taking logs base 3 of both sides would be awkward, because it would be awkward with the 2, and taking log base 2 of both sides would be awkward. So what we do is we take the default base of both sides of this equation. So we use log base 10 of both sides of this equation. As long as we do log with the same base to both sides, then we are keeping the equations, both sides of the equations, equal. So I'm going to take log base 10 of both sides. So that's log of this expression 3 to the power of 5 minus x is equal to log of this expression 2 to the power of 5 plus x. Since both expressions are equal, since that is equal to that, then the log of both of them will be equal. Remember that if I don't have a base, then it is the default base 10. Okay, so if it just says log, it means log base 10 of that thing. Okay, now I need to use one of the log laws. And the log law that I'm going to use is the third one. I know that log of a to the power of n is equal to n multiplied by the log of a. That allows me to remove the exponent from within the logarithm. Okay, so how does that look on this one? Well, our n in this question in this logarithm is 5 minus x. So removing it outside, it becomes 5 minus x multiplied by the log of 3. And the right side of the equation, 5 plus x is my exponent. 5 plus x multiplied by log of 2. So I've just applied this log law, rewriting the logarithms as I've done. Now, what we do is we multiply out the brackets. 5 minus x lots of log 3 is the same as 5 lots of log 3 minus x lots of log 3 equal to 5 lots of log 2 plus x lots of log 2. It's better to write x log 3 than log 3 times by x, because if you write log 3 times by x, people might think that's log of 3x, when in fact you mean log of 3 multiplied by x. So that would need us to use brackets to make sure we understood what we needed. But if we put the x first, then there's no need for that. Okay, so x log 3 is the better way of writing log 3 multiplied by x. Okay, now what we need to find the value of x. So the best thing to do is make sure we have x all together on one of the sides of the equation. I've got a negative x log 3 on the left side and a positive x log 2. I prefer having positives as far as I can get them. So I'm going to add x log 3 to both sides. I'm also going to subtract 5 log 2 from both sides, so that all the constant values, because 5 log 3 and 5 log 2 are just constant values. You could evaluate them on your calculator. So my next line will be 5 log 3 minus 5 log 2 is equal to x log 2 plus x log 3. And since I want to find x, it's in effect me making x the subject of this equation. To do that, I need to factorize the x from both of these expressions. So on the left side, I get 5 log 3 minus 5 log 2. The right side, I get x lots of log 2 plus log 3, which I can simplify. Log 2 plus log 3 is log 6, but I can leave it separate. It doesn't really matter. My calculator can deal with both versions. And finally, divide to get x on its own. So x is equal to 5 log 3 minus 5 log 2 divided by log 2 plus log 3. And I can just enter that as it is onto my calculator and get my answer to 3 significant figures because that is what I was asked for. So that to 3 significant figures is 1.13. So that is the solution to my equation to 3 significant figures. So running through that again, firstly, because there were different bases on each side, we took a default base of log base 10 of both sides. Then we applied the log law that allowed us to remove the exponent out of the logarithm. Then I expanded the brackets, rearranged, and tried to make x the subject of the equation. And once I did, I could then evaluate the answer using my calculator. Okay, have a go at this similar question. Solve this equation to 3 significant figures. 4 to the power of 6 plus x is equal to 5 to the power of 11 minus 2x. Pause the video, have a go, and then I'll show the solution. Okay, the solution to this. So firstly, take log of both sides, and then I'm going to show fewer steps than the previous one. Take log of both sides and then remove the power out of the logarithm so that you'll get 6 plus x multiplied by log 4 is equal to 11 minus 2x multiplied by log 5. Expand the brackets, simplify, and make x the subject of the equation. You will get, as I said, I'm going to show fewer steps. You are going to get 2x log 5 plus x log 4 on the left equal to 11 log 5 minus 6 log 4 on the right. Then take a factor of x out. You get x lots of 2 log 5 plus log 4 equal to 11 log 5 minus 6 log 4. We can simplify these logarithms into single logarithms if we wanted to, but we don't need to. So then x is equal to 11 log 5 minus 6 log 4 over 2 log 5 plus log 4. And that, to 3 significant figures, is 2.04. If you got that right, well done. Okay. If you need me to explain a little bit more, please in the comments just write down, and I will. Okay, the third of 4 different types of equations. So this third one, solve fully with answers to 3 significant figures, the equation 3 to the 2x minus 2 lots of 3 to the 1x minus 15 is equal to 0. Now, when you've been doing maths as long as I have, as soon as you see something like this, you think quadratic. This is a hidden quadratic, where you have an unknown thing and then an unknown thing to the power of 2. Okay, so it's of the form a squared minus 2a minus 15 equals 0. That's what this looks like to me, where my unknown thing a is 3 to the power of x. Because if I have 3 to the power of x, if I square 3 to the power of x, using index laws, when you have a power to a power, you multiply. So 3 to the power of x, if I square it, is 3 to the power of 2x. So really, what I have here is 3 to the power of x squared minus 2 lots of 3 to the power of x minus 15 equals 0. So I'm going to solve it like I would a quadratic. Firstly, I think, can I factorize? And yes, I can. So factorizing a quadratic, you take the unknown thing that is squared and you put, if it's just that unknown thing squared, so if you just had x squared, then you would have x in the start of each bracket. Here, the unknown thing, 3 to the power of x, is being squared, so it's 3 to the power of x at the start of each bracket. Because 3 to the power of x times 3 to the power of x will be 3 to the power of x squared. And then you're looking for two numbers which multiply to make minus 15 and add to make negative 2. So that would be positive 3 and negative 5. So that is the factorized form of my quadratic equation, my hidden quadratic equation. So now I know that these two things multiply to make 0. So either the first one is 0. If the first one is 0, then I know 3 to the power of x has to equal negative 3. If the second one is 0, then I know that 3 to the power of x has to equal 5. Now have a think. Do both of those work? Can 3 to the power of x be both of those values? Think back to your exponential graph. When we started doing exponential functions, we sketched the graph of y equals 3 to the power of x, and it looked like this. It approached, as you headed off to negative infinity, it approached the x-axis but never reached it. Can 3 to the power of x equal minus 3? Can the y value ever equal minus 3? And the answer is no. So that will not have any solutions. So we ignore that one. But it's best to ignore it by explicitly showing that you have ignored it, that you've thought about it, and you have discounted it. 3 to the power of anything cannot equal minus 3. The other one, 3 to the power of x is 5. Well, yes, there is a value of x which would give you 5. We just need to find that value of x. To do that, we need to use logarithms. So x is equal to log base 3 of 5. So that's just the other way of writing that expression 3 to the power of x is 5 is by saying that x is equal to log base 3 of 5. It is the power that you would put 3 to get 5. And that is the definition of what it is. And that is equal to 1.46 to the power of 3 significant figures. And that's our answer to this question. Okay, so have a go at this similar hidden quadratic here. Solve fully with answers to 3 significant figures, 2 to the power of 2x plus 3 lots of 2 to the power of x minus 18 equals 0. Pause the video, have a go, and then I'll show the answers. Okay, so the answer to this, firstly, you factorize this because this is the same as 2 to the power of x squared plus 3 lots of 2 to the power of x minus 18 equals 0. So your unknown is 2 to the power of x. So if I factorize it, I'll have 2 to the power of x in both brackets. Multiply two numbers to make minus 18, add to make 3. One of them is going to be positive 6. The other one's going to be negative 3. So either 2 to the power of x is negative 6 or 2 to the power of x is 3. Now 2 to the power of x cannot be negative, so that one is discounted. 2 to the power of x is 3. That's when x is log base 2 of 3. And that, to 3 significant figures, is 1.58. If you got that answer right, brilliant. If you didn't, that's okay as long as you understand it. Okay, here's the last type. Now, in a previous lesson, we did a question where we solved this using trial and error. Now we're going to actually use logarithms to find the exact time at which my investment of £700 into a 5% savings account reached £1,000. Okay, so the way to do it, we want to solve when the value is £1,000. So we're trying to solve the equation 700 times 1.05 to the power of t equals 1,000. At this point, people might be tempted to use logarithms. And that you can, as long as you do the same to both sides of an equation, it is okay. But at the moment, I would firstly find out what 1.05 to the power of t needs to equal. Firstly, divide by 700. So 1.05 to the power of t is 1,000 divided by 700, which is 10 sevenths, which is 1 3/7, like 1.428, something like that. Okay, but 10/7 is exact, so let's leave it at 10/7. Then we use logarithms. So t is the logarithm to base 1.05 of 10/7. So the time when my investment reaches £1,000 is 7.31 years to three significant figures. So 7.31 years after I've put my money into my account, it'll reach an investment of £1,000. Okay. All right. Have a go at this one. So this was your turn before, but before you found out that when the bacteria reached 1 million by using trial and error. Now you're going to do it using logarithms. Find the exact time when the bacteria in the Petri dish reached 1 million bacteria. So the equation was, for the number of bacteria, was 5,200 because that's how many you started with, and it was increasing by 20% every hour. Therefore, the number of bacteria in the Petri dish was 5,200 times 1.2 to the power of t, where t was in hours. So when do the number of bacteria reach 1 million? Pause, have a go, and then I'll show you the answer. Okay, so the answer to this, you firstly set 5,200 times 1.2 to the power of t equaling 1 million. At this point, you divide by 5,200, so 1.2 to the power of t is equal to 1 million divided by 5,200. And so then to find t, you do log base 1.2 of that answer, of that value. And that is to three significant figures, 28.8 hours after you start cultivating the bacteria in the Petri dish. Okay, if you got that right, superb. What you should do now is you should practice all different types of these questions. There are some lovely questions in exercise 12.4 of this textbook. So the fourth exercise in chapter 12. And so practice until you feel fluent in using logarithms to solve equations where the unknown is in the power. Okay, off you go and enjoy.